Hello everyone, and welcome to a geostats lecture video. And in this lecture video, I want to walk through the first part of dealing with a basic linear regression in R. And that's going to involve testing the data to make sure that we are actually meeting the assumptions that we need to meet to be able to actually move forward with a regression. And so what I've already done is I've set up the packages that we're going to need. We actually don't need GIS tools. We need a ggplot2 to do some of the QQ plots. And then this core plot package here is going to be used to do some of the multiple correlation calculations and graphics. So anyway, what you're going to do is, if you don't already have these two packages installed, I would recommend that you quickly install them. So I'm going to run this just to make sure that we have our packages installed. Okay. So, like I said, in this video we're going to be testing the assumptions of regression. Okay. Oops. So basically, as a general rule, regression requires three things. It requires normality, a linear relationship, between the dependent variable, which I'll call the dv, and all independent variables, which I will be calling iv. And then it also requires a lack of collinearity between all iv. Basically, what that means, I might have spelled collinearity wrong, but that's okay. Basically, what this assumption is saying is just, it's the idea that we don't want to be having our independent variables related to each other, because then you're essentially double counting certain variables. So for example, if you have two variables that are providing the same information, right, you're double counting or you're doubly weighting that information in your regression. So this lack of collinearity is just a good base check. So first of all, let's start off with normality. Well, actually, before we do anything, let's load the data. So what we're going to do is we're going to be using the iris dataset that comes preloaded with R. Okay. And then what I want to do here is I actually want to subset out just the setosa. Actually, just really quickly, let's take a look at the iris dataset. It's been a while since you may have worked with it. We have essentially 4 variables that are numeric, and we have 1 variable that is categorical. And the species, there are 3 species in this dataset. And so what I want to do is actually want to remove the species label from the data set, so that way we don't break some of our code later on. And I also want to subset only one of the species so that we don't have a unintended consequence of having the different species interacting and affecting the relationship, because we're not going to be modeling a categorical variable. So what I'm going to do here is I'm going to call a new variable called setosa. I'm going to set that equal to iris dataset index for iris $species, because again we want to pull out the species is equal to, and we want setosa. Okay, and then we want to remove that 5th column. Okay, so this is going to subset only setosa and remove species label. Okay, so if we run that, we should get setosa, which now has 50 observations and 4 variables. Good. Now, what I want to do here is I just want to quickly grab the names of setosa, because I have a tendency to make all kinds of spelling mistakes. So now I have these in my back pocket so I can copy and paste them. So let's first start with normality. So we've already kind of done normality when we talked about exploratory data analysis. But I want to refresh it here by doing the visual check which is going to be the QQ plot. So we'll call it QQ. And I'm going to use the ggplot functionality here. We're going to have the data equal to setosa. Then we're going to have the mapping, which again tells you what variables are going to be driving the thing. And in this case, because we're doing a QQ plot, we have to give it a sample. And that sample is going to be equal to, this is where I always mess up, so we're going to copy directly. That way there's no errors. Okay. Then we need to add two things. We need to add the geom underscore QQ. So this is going to put the points, and then we need to add the geom underscore QQ line. So this is going to add that that trend line. I have done something wrong. Oh, oops. I forgot the AES there. There we go. So now if I plot QQ, you can see here that we actually are really close to the line here, which is a really good indication that our data is actually normally distributed. So we can do our statistics test, stat test, and we're going to do the Shapiro-Wilks. So I'm going to call from the stats package the Shapiro test, which takes in the variable of interest. So in this case, it's going to be setosa $sepal length. Okay, so we can run that. And you'll see here that we have our test statistic, and more importantly, we have this p-value here that is statistically insignificant, which means that our data is normally distributed. So in this case, this is a good sign. It means our data is normally distributed. Okay. So you would repeat this for all of the variables of interest. In this case, I'm only going to do it for the dependent variable in the interest of time. So now we're going to do a quick check of our linear relationship. And I want to show you this in two ways. The first way is going to be on an individual variable. And I'm going to call this core underscore plot. So this is when you would want to compare the dependent variable to one independent variable, or compare two different variables. So this is going to be basically, we're going to be creating a scatter plot. So ggplot data is going to be again equal to setosa. So in this case, we're going to be mapping our x and our y. Our y is going to be our dependent variable, which in this case we said is going to be sepal.length. Now the variable that we're going to examine first is going to be sepal.width. Okay. So we have our y, which is our dependent, and we have our x, which is our independent. And we're going to throw onto that the geom underscore point. So if we run that, we don't get any errors, which is always a good sign. And then we call plot core underscore plt. Okay. So it definitely appears that there is a general linear trend, positive linear trend. Okay, that makes sense. What we can do though is we can take this a step further again. So just like before, right? This is our visual, and we can follow that up with a statistic. And our statistic is going to be a correlation, or Pearson's correlation coefficient. Okay. And so the way we're going to do that is we're going to call from the stats package a function called core.test. So you know what? Since we're calling something new, why don't we actually look at it? Core.test. All right, so this is testing for the association between two samples. So in this case, it's going to be our independent variable and our dependent variable. And basically, we don't need to worry too much about it. We're going to keep the defaults pretty much by default because we're going to be testing Pearson's correlation. And all we have to really worry about are the x and the y, which are the two variables of interest. So stats core.test takes in an x and a y. And our x variable is going to be we're just going to copy and paste these because we want sepal width and sepal length. But we have to actually pass in setosa first so that we actually grab the proper data frame, because these things don't exist on their own. Okay, so again, this is going to perform that Pearson's correlation coefficient. So if we run that and we don't crash, so if we call core, you'll see here that what we have is we have our correlation, so 0.74 right here. And this is sort of telling us that we have a t-test and that the value is statistically significant, which basically means that this correlation is strongly positive and it is significant. Okay, so we now have a visual and a statistical rationale for saying that our data are good to go. So we can also do this in mass. And what I mean by in mass is we can look at the correlation coefficients and we can look at the plots for a bunch of variables all at once. And the way we do that is by calling by calling the function core from the stats package. Okay, so let's just call it core. Okay, so what core is going to do when you pass in an x, where x is a data frame, it's going to spit back the correlation of all of the different columns in that data frame. So if we do core x equals setosa, and we run this, we spit cores. Right, you'll see here that this right here, this 7.42, this is the same correlation coefficient we got before. So between sepal length and petal length, we have 0.26, and between sepal length and petal width, we have 0.27, and so on and so forth. So this is also the way that we would check for collinearity. Right, we would check to make sure that none of these other columns, so between, for example, petal width and petal length, we want to make sure that there's no high correlation coefficients between other variables that we're not interested in. So for the sake of argument, we're going to say that we're going to use sepal length, and then petal width is going to be our first variable, and then when we decide to do multiple, we'll actually include petal length as our second variable. Okay, so hopefully that makes sense. So again, just to recap what we've done here, we've tested for normality, both with a visual check and a statistical check. And then we checked for the relationship between our dependent variable and our independent variable. In this case, just comparing one. And then with, we can also do it for multiple with the core function. And then if we just pass in the name of the data frame into the default plot function, you'll see that what we get here is a small multiple. So this is the plot comparing sepal width on the y, or sepal length on the y with sepal width on the x, petal length and petal width. Okay, so this is a quick way of just seeing all the variables, so we can compare this with our correlation coefficients to sort of get an idea of the relationships and make sure that they're generally linear. So this relationship right here is definitely our best bet, and then we're going to introduce this one in as our secondary. So hopefully that made sense. I know this was a lot. Hopefully most of this was a review in terms of the R code, but if you have any questions, please reach out. Thank you.